I want to talk a little bit more about the transfer function, h of s. When we look into circuits, we'll see that we'll be able to find the transfer function directly from circuit analysis. Another reason why it's so important. But h of s is defined as the ratio of the Laplace transform of the output to the Laplace transform of the input, and this is with zero state, or in other words with all initial conditions set to zero. So again, h of s will not depend on actually the form of the output or the form of the input. It will depend only on the coefficients and the order of the differential equation. Once we have the transfer function, we can then find the zero state response for any input just by multiplying our transfer function times the Laplace transform of the input. Then we can take the inverse Laplace transform. In this particular case, going back to the time domain, we know that multiplication in the Laplace domain actually transforms back as convolution. So I can write y of t is going to be the inverse Laplace transform of h of s convolved with x of t. But we also know from previous chapters that we can get this zero state component, y x of t, by convolving h of t with x of t. So by comparing these two expressions, we see then that h of t, the impulse response of our system, and h of s, the system transfer function, are a Laplace transform pair. So it was no accident that I chose to use capital H for the system transfer function, because I knew that it would turn out to be equal to the Laplace transform of our impulse response. I mentioned previously that we would see later on how to find the impulse response. Well, this provides a method. We'll see soon how to determine h of s for a particular circuit using circuit analysis. We can then take the inverse Laplace transform of h of s to get find the impulse response. Looking at that same problem again, we could find the zero state response now using convolution. So from our original differential equation, which was this, we have found already, we can write down almost directly from the differential equation what h of s is. So again, this is all done for the zero state response, so all the initial conditions are 0, and capital Y and capital X, and so I can get the system transfer function, which is the y over x. That's going to be s plus 1 over s squared plus 4s plus 4. So we can see how the numerator polynomial in my transfer function is determined by the right-hand side of my differential equation, while the denominator polynomial is determined by the left-hand side. And I can factor the denominator as s plus 2 squared, and write that as in partial fraction expansion. This would be 1 over s plus 2 minus 1 over s plus 2 squared. So the corresponding impulse response of this system would be the inverse Laplace transform of each of these terms. First term is inverse Laplace transforms as e to the minus 2t u of t, and the second term has an inverse Laplace transform of t e to the minus 2t u of t. Okay. Now I can get, for my given x of t equal to e to the minus t u of t, I can, from my convolution table, carry out the convolution of h of t and x of t, and with a little bit of algebra, what I get from this is just t e to the minus 2t u of t, which again is my zero state response. So yet another way to solve this problem using the impulse response in convolution.